Hello and welcome to BioRules video lessons. This is also kind of a high-level class. Actually, it's a repetition of what we saw in the photosynthesis overview, but we are going to take a look on a closer approach on the idea on how the excitement of chlorophyll happens. Okay, so light and electrons. To exemplify what happens in chlorophyll with photosynthesis, I'm going to be talking about fluorescence. Fluorescence is a phenomenon that we see in watch dials. Sometimes we have those little stars that you put on the ceiling. In those kind of chemicals, when an electron receives a photon, this electron might be excited, gets more energetic, and it may jump to a more energetic shell or a layer or orbital. When that happens, so you have a more excited electron. In the moment you stop adding light, then the other way around happens. The electron jumps back because not excited anymore to stay in a more energetic orbital. So it jumps back to the original orbital. But in that process, it emits a photon, and then you see the dial in the dark. So during the day or when you're adding light, the electrons are jumping, they go for the more excited orbital, and then in the moment that you turn off the light and they stop receiving light, these electrons jump back and they emit a photon. So this is the process of fluorescence. The idea with chlorophyll is going to be quite similar, okay? But what will happen there is oxidation. And if you remember, oil rig, oxidation is loss, reduction is gain. So what happens is that an excited electron that is hit by light, it jumps to a more energetic layer, it jumps to a more energetic orbital. However, if this excitation is quite big, like what happens in chlorophyll, these electrons might jump out of its orbital and actually jump out of this atom. So in this case, light makes that atom to suffer oxidation. Oxidation is loss. So basically it gives away the electrons. In chlorophyll, the electron will be given away, and then chlorophyll has to steal electrons from water to be able to replace what it has just lost. So water is broken down, making oxygen gas, O2, and releasing some protons around. Okay? So this is the process of oxidation by light that happens with chlorophyll. So talking about chlorophyll, in the photosynthesis overview, I showed this molecule already. Here it is again, lots of nitrogens, carbons, oxygen, and hydrogen. But also in the heart of chlorophyll, we have a metal. We have magnesium. So magnesium is one of those elements that we have a little bit in life, but without it, no photosynthesis, no life as we know it. So it's a very important element in biology. There are two versions of chlorophyll that are important for us. The ones that have a CH3 over there is a chlorophyll A, and another one that instead of the CH3 has a C double O and hydrogen, which is chlorophyll B. So those two chlorophylls together, they are going to be absorbing light by being excited and jumping electrons and then stealing electrons from water and doing all the process of photosynthesis that we saw before in the photophosphorylation. Okay, the light, the visible light has a spectrum. We saw this here before. We have around there 400 nanometers. The limit of the visible is 380 nanometers, is the limit between ultraviolet and violet. 400 is a kind of violet, 450 is a bluish. And then you have 550, which is now in between those two over there. We have 550 here. We have the green light. And above 700, we have the red light. So, and the limit here is about 760 or something around that. Okay, so this is the visible light. The sunlight that comes from the sun has a fairly homogeneous distribution of different wavelengths, make it quite white. So what happens then when this white light hits chlorophyll? On this axis, on the y-axis, we have absorbance, so how much light is being absorbed. In the x-axis, we have the wavelength, so how much absorption is happening, causing photosynthesis by chlorophyll A and chlorophyll B together. As you can see here, there's a peak around the red, 600, almost 700 nanometers, that's red, and you have here around the 450, it blue. Let's make it blue to make it prettier. So we have here it blue. And around 550, we have a bunch of green that hits the chlorophyll and is not absorbed, is reflected. That's why we see chlorophyll green. That's why we see plants green, because they reflect green light. They do not absorb it. So it's not used by plants, most of the green light. They use a lot of blue. They use not so much, but still a lot of red and almost no green. Okay? So if you put them both together, chlorophyll A and chlorophyll B, we have they are slightly different between themselves. Chlorophyll A has that curve that's more or less same between blue and red. Then chlorophyll B has a bigger peak in the blue than it has on the red. So as a result, the chlorophyll B is a little bit more twisted to the side. The chlorophyll B is more twisted to the yellowish here, while the chlorophyll A, it absorbs red and blue, so it's a little bit more twisted to the bluish side here. As a result, this will create shades of green depending on the proportion of chlorophyll A and chlorophyll B that you have in plants. Some leaves are going to be looking darker, more bluish green, while others are going to be looking more yellowish green, depending on the proportion of chlorophyll A and chlorophyll B that we have. Okay, just to illustrate, chlorophyll here comes in the photosystems. Chlorophyll are going to be present in the photosystem 2, the first one to excite and lose electrons and get electrons from water. So we have here no water being broken down. And chlorophyll will also be present in the photosystem 1, the one that re-excites the electrons to be able to give it to the NADP, making NADPH. So this here is the idea with chlorophyll. Not much, but quite interesting class. I hope you got the idea, and I'll see you in class. Bye bye.